Hi, welcome to my channel. In the previous video lectures, we have seen tanh and sigmoid function and at their associated vanishing gradient problem as well. Now let's move on to the one of the most important activation functions used in modern deep learning, the RELU or Rectified Linear Unit. RELU is mathematically defined as f of z equal to maximum between 0 and z. The intuition is very simple. If the input value is positive, ReLU passes it as it is. If the input is negative, it blocks the value and outputs 0. Because of this simplicity, ReLU allows very fast training and works extremely well for the deep neural networks. Another major advantage is that ReLU does not saturate on positive side, which helps reduce the vanishing gradient problem. However, ReLU has one of the important drawback called the dying ReLU problem, where some of the neurons get stuck outputting 0 and stop learning. To address the dying ReLU problem, a small modification was introduced called Leaky RELU. In standard ReLU, the negative values are completely blocked. In Leaky ReLU, instead of 0, a small slope is allowed for negative values. This ensures that neurons still receive a gradient even when the input is negative. Leaky RELU has several advantages. It prevents the dying ReLU problem, it allows continuous gradient flow, and in some cases, it converges faster than ReLU. It is also simple to compute and computationally efficient, making it suitable for deep networks. Next, let us discuss the ELU or exponential linear unit. ELU behaves like ReLU for positive input values, but for negative inputs, it uses an exponential curve. Mathematically, f of x equals to x when x greater than 0 and equal to alpha times e to the power x minus 1 when x less than equal to 0. Here, alpha is usually set to 1. Unlike ReLU, ELU produces negative outputs, which helps bring the mean activation closer to 0. This reduces bias shift and improves learning speed. However, ELU is computationally more expensive than ReLU because it uses the exponential function. Now let us look at a modern activation function called GELU, Gaussian Error Linear Unit. Instead of using a hard threshold like ReLU, GELU uses a probability-based gating mechanism. GELU soft decides how much of the input should pass through based on probability rather than a strict cutoff. Because of this smooth behavior, GELU is a non-linear, probabilistic, and performs extremely well in deep models. In fact, GELU is the default activation function used in Transformers and BERT models. Now we move to the softmax activation function, which is mainly used in the output layer of the neural networks. In classification problem, the network must decide which class an input belongs to. Softmax helps do exactly that. It converts a vector of real numbers into a probability distribution where all the output values lie between 0 and 1. The sum of the probabilities is exactly 1. The input vector z equals to z1, z2 up to zk. The softmax is defined. Softmax z I equals to e to the power zi over summation j1 to k e to the power zj. Here k is the number of classes, zi is input score, is called logit. The exponential function ensures that all outputs are positive, larger scores get much higher probabilities, small differences between logit becomes more visible. Let us understand softmax with a simple example. Suppose the output layer gives z equals to 2, 1 and 0.1. After applying softmax, we get 0.66, 0.24, 0.10. Here, class 1 has highest probability, so it becomes the predicted class. This is how softmax helps in the neural network make multi-class decision. To summarize, ReLU and its variants are used in hidden layers, while softmax is used in the output layer for classification.